What we see here is a logic circuit consisting of a line of alternating AND and OR gates. Such circuits appear in all complex calculations, for example in the carry operation for binary addition. In order to obtain a result, up to 5 nets along one of the paths beginning in A and B have to be charged or discharged. The speed of the chip depends directly on the lengths of the paths and on the depth of the whole circuit, in this case 5. We can, however, perform exactly the same function with the circuit shown to the right. This may seem surprising at first glance. However, we can verify the equivalence by giving the input pins A to F all possible combinations of zeros and ones, and checking that the outputs are the same. As an example, we will do this for just one choice of ones and zeros. We will start by analyzing the left circuit. As the input at C is 1, the first OR circuit will yield 1 as a result, no matter what the inputs at A and B are. As both inputs of the following AND circuit are 1, it yields the result 1. This leads to the result 1 at the following OR circuit, no matter what the input at E is. Finally, both inputs at the last gate are 1, and thus the output on the left circuit is 1. Next, we will analyze the right circuit. Look at the gates directly behind the inputs. As the inputs at C and D are both 1, the first 2 OR gates will both yield 1, so the third will as well. As the input at F is also 1, the right AND gate yields 1 and thus also the final AND gate. We have shown that this input yields the same answer for both circuits, namely 1. As there are 6 input pins, there are 2 to the power of 6, that is 64 different entry combinations, all of which we could check in this way. For a large number of input pins, this method would take much too long, even for a computer. In fact, the problem of whether or not one can check quickly whether 2 logic circuits are equivalent is one of the great open problems of mathematics. The right circuit has smaller depth, namely 3 instead of 5 steps, and thus is faster. As not more than 4 input pins can be combined with a depth of 2, a depth of 3 is optimal in this case. Typically, the input signals for an AND OR path are the results of earlier gates and have traveled different distances on the chip. This means that the input signals are not usually available at the same time. If, for example, the signal arrives very late at F, the left circuit could be faster because there is just one remaining gate step to traverse. Unfortunately, no algorithm has yet been developed which finds a circuit of optimal depth for a given AND/OR path of the length n. But we can very quickly compute nearly optimal circuits, even for arbitrarily chosen signal starting times. The algorithm used for this is asymptotically optimal and very fast. Many logic circuits for high-performance processors are optimized in this way.